So the title of my talk today is Applications of Black Hole Scattering. Before I mention what scattering is, of course, one has to first understand the free theory. So I'm first going to start with the free theory, which is free fields in the presence of black holes. And then I'll develop some story of how scattering can be understood in the presence of black holes. This talk is mostly based on work with a great PhD student in Utrecht, Nico Kumenboom, a couple of papers that we wrote in December 2012, and one in October last year, and one that should be out in a couple of weeks. Also another paper with Nico and Regulator. Towards the end of my talk, I'll mention some things about some work that I've done with Panos Betsios and Olga Papadoulaki, who are both postdocs now in Canada. And in the end, one of the applications that I'll refer to is some upcoming work with a graduate student in Brussels, Ankit Agarwal. Hopefully that should also be out in a month or so. So as I said, let's study the free field theory. I suppose most of you are familiar with essentially everything that I'm going to say will only require quantum field theory and curved spaces, so general relativity. So if you have anything to object to at any point during my talk, please feel free to stop me and complain. This is a picture that I stole from Hawking's paper. So what he considers here is some infalling matter that's depicted by these curved lines here that collapse to form a black hole. And that's the singularity at the center. This is in Eddington-Finkelstein coordinates. And the thick line that you see here is the event horizon. And so there's matter that's coming from past null infinity. And now he focuses on what happens if you quantize the scalar field. So this is scalar matter that's falling into form a black hole. And the question is what happens if you quantize the scalar field in the presence of a black hole background. What Hawking found was first that the modes that you expand your field in on past null infinity and future null infinity are different. So what he did was he took modes that are formed on future null infinity, traced them back. It's called the geometric optics approximation, where essentially he just said that to first order, leading order approximation, these scalar fields, I'm going to treat them as free fields. So he just traces them all the way back, and you see that all the modes that start or that finish on sky plus trace all the way back, and they get concentrated near the horizon. And he says if the horizon is large enough, the black hole is big, then nothing really happens. These free fields just continue all the way back to the asymptotic past. So he has some map of how the modes from future infinity go back all the way to sky minus, so past null infinity. Now he has a way of comparing modes that you sent in to those modes that you receive at future infinity. What he then found was that these modes were related by some thermal prefactors. So he found that there's particle creation in the theory. So you send in some matter, some other matter shows up, which is imperfect black body radiation. So he concluded that no matter what you throw into the black hole, you're going to lose information because all you get out is just thermal spectrum. So the question now is what I want to do, the ethos of my talk and the entire program that I've been working on is to understand whether this theory is valid, whether you can just approximate free fields to be free on this background. And the basic claim that I want to make is that as long as fields are far away from the black hole, you're justified in just using free fields. But as you get these fields closer to the horizon, the premise of my entire talk is that the metric isn't static, it's not fixed, that the metric fluctuates at a quantum level. And so what I want to say is that these gravitons, which are fluctuations of the metric near the horizon, interact with the scalar fields, and these generate scattering amplitudes, which are not just in the free theory, but they're interacting. And this makes everything that I'm going to say is how to incorporate these interactions into the theory, into Hawking's calculation. And the question will then be, how dramatically is Hawking's theory violated, or at what point do you get a change in Hawking's understanding of the free field theory and the thermal spectrum? And do you get unitarity? Do you ever get information out of the black hole? Can these interactions of near horizon fluctuations be good enough for us to describe any unitary scattering process? Are there any questions so far with just the general ethos of what I'm going to do? Okay. So as I said, we're not interested in the free theory, and perhaps a lot of you work on classical collapse problems know this much better than I do. That if you have matter that's collapsing, as long as the impact parameter of the particles that are infalling is small enough, then you form classical black holes. So at some point, whatever small enough means, I will try to carefully quantify this through the talk. Whatever the small enough impact parameter is, at some point, if the impact parameter of particles is small enough, you start to form black holes. So you cannot ignore gravitational interaction. So the question is again, can we compute scattering amplitudes? So why would such a regime exist? A regime where you can effectively compute scattering amplitudes? There are a couple of things that one could say, sort of heuristic. One is that there are indications that the information paradox or the information problem of Hawking is resolved in effective theory. And this comes mostly from holography or ADS-CFT and string theory. So the details are unimportant, but there's just some popular belief that the information problem is not something that's necessarily resolved by some Planckian physics, but already appears within effective field theory. So at some scale, but you don't have to go all the way to your UV cutoff. Another way of saying this is that if you form a large black hole which has some large entropy, a lot of thermal radiation, if all the information is stuck in some ultraviolet physics, that means that you let the black hole radiate until it becomes small enough with Hawking radiation, and only when the black hole becomes Planckian or hits your ultraviolet scale, that's when all the information is going to come out, and because only your ultraviolet physics is resolving your information problem. That would be a way of saying that something that's very Planckian, very small, captures an enormous number of degrees of freedom, which we don't necessarily think is the reasonable resolution. Another reason why such a regime would exist is that gravity is special because of the dimension full coupling constant. It's that quantum effects arise not just from large momentum transfers like in quantum field theory, but also from emergent scales. Hawking's problem itself is a manifestation of that, because you have a Schwarzschild radius that's very large, that's visible in effective theory, that already causes problems when you try to quantize scalar fields in the presence of this black hole. So there are a couple of reasons why you would expect that in the effective theory, why such a regime where you can calculate amplitude should exist. So what I want to do in this talk is to define this regime in effective field theory. So I'm going to use phase space variables. So like what you would do in quantum field theory, using Mandelstam variables, properties of the scattering amplitude. And I want to calculate or discuss some calculations of some amplitudes in the background and what they imply. Very interesting things appear in the presence of black holes. So some applications that I will discuss are gravitational echoes. Some of you may be familiar with them. So this seems to be a very natural place where even though you have a black hole, which you naively classically think of as just having infalling boundary conditions at the horizon, because of the scattering process near the horizon, there's also outgoing quantum radiation that is correlated unitarily with the infalling matter. So it pretends like there's some, what you would otherwise think of as an exotic compact object that has some boundary conditions that reflect this matter. And so you can incorporate this scattering matrix near the horizon as some kind of a boundary condition that scatters particles back. And with the light ring that's further away from the horizon, you have a problem where echoes start to leak out like you would have for quasi-normal modes. And there are also some interesting applications like an emergence of soft theorem. I'll explain, for those of you that are unfamiliar with them, I'll explain briefly towards the end what Weinberg soft theorems are in flat space and how there are new soft theorems that emerge in the black hole that are different from Weinberg soft theorems. So here's a plan for the talk. I'll first discuss what happens when you have no black holes, nothing dramatic happening, where impact parameters are very large, things are simpler. And then I'll slowly build towards smaller impact parameters, and then discuss how scattering amplitudes show up and some applications towards the end. So here's a start with large impact parameters. What I mean by large impact parameters is just think of a Penrose diagram where you have two light-like particles or particles with very low mass that are traveling. They look like they collide head-on, or not head-on, but they look like they're hitting each other on the Penrose diagram. But this is a conformal diagram, so they're transverse separated. So the impact parameter you want to think of as the transverse distance between these two particles. So naively, if you have not energetic particles that are traveling very far from each other, you would say they're just not interacting. They're just moving past each other. Now you can ask the question, let's leave them to be transversely separated by a large distance, but start increasing the energy at which they're traveling. So you would have an increasing energy of center of mass energy of this collision. And the statement is that even though you have a large transverse separation, there's still gravitational interaction. That does not change the momentum. There's not a lot of transverse momentum transfer. but there's some graviton exchange because of the back reaction and the geometry. So you can also think of this as a classical solution to Einstein's equations, and this is called the Eichelberg-Sechsel Shockwave. What happens is neatly shown in this picture. Take a red particle that's moving along some null path. The green test particle that we're looking at gets kicked along the longitudinal directions, and then after it's crossed the red particle, it just continues as if nothing had happened. But the geodesic of the green particles get changed along the direction of the red particle. So again, as I said, there's no transverse momentum transfer. The dominant effect is the longitudinal one along the direction. And you can see from the blue equation at the right top that the amount that the particle gets kicked is proportional to the momentum of the red particle. So the higher the momentum of the red particle, the more it gets kicked. And of course, this is only possible because we have G Newton, which is a dimension-full quantity. You can
the red particle has energy, and the green particle is that particle.
That's right. That's right. Of course, the green particle also, if you treat both of them democratically, the green particle would also kick the red particle along its direction. So you can ask whether you can represent this interaction, this gravitational interaction, in Feynman diagrams. And the answer turns out to be yes. And it's actually beautiful and rather simple. So what we have is flat space before any particles are moving on it. So we're going to do work in the background field method. So you take your Einstein-Hilbert action that is minimally coupled to a scalar field, and then you expand your Einstein-Hilbert action around flat space, and H nu would then be your metric perturbations. And to leading order, you have a cubic interaction where the graviton talks to the stress tensor of the scalar field. This comes from the minimal coupling in the action. And this generates for you a 3-vertex. So something of this kind, where the stress tensor is quadratic in the scalar fields. So at every vertex, you have 2 scalar fields and a graviton. And you can ask yourself, what are the Feynman diagrams that I can build out of such an interacting theory? And the dominant ones, where you found the transverse momentum transfer to be small, so where S is much bigger than T, turn out to be what are called the ladder diagrams, because they look like a ladder. So there are 2 one-loop diagrams, 6 two-loop diagrams, and so on. What's remarkable about this limit, it's called the iconal regime, is that all these diagrams can be explicitly calculated to infinite order, so infinitely many loops, and you can resum all of them and write a simple enough amplitude for this interaction. So that amplitude looks like so. It can just be explicitly written down. So all the parameters that you see in this amplitude are things that I've told you. G Newton is just what it is. S is the square of the center of mass energy of collision. There's this interesting parameter mu, which is an infrared regulator for the graviton mass. The reason why this is necessary is because, as we said, the graviton itself does not carry a lot of momentum. So the theory is projected onto the soft sector, meaning that the graviton carries very little momentum. And in the infrared, when the graviton is on shell, because it's a virtual particle, there's a divergence from the propagator. So you need to cut it off somehow. And the standard thing to do is to introduce a regulator. There's a very interesting series of papers in the last, say, 8 or 9 years, where people try to understand why such infrared divergences appear, because they shouldn't be physical in amplitudes. And the answer turns out to be that if you treat your vacuum in quantum field theory at asymptotic spatial infinity, which is what we do in field theory, in quantum field theory, but this is the wrong vacuum to work in quantum gravity. It does not respect all the symmetries of infinity. And the correct problem in gravity is the one where the vacuum is defined on Scri minus or Scri plus, but not at spatial infinity. So past and future null infinity. And there are additional symmetries that emerge, so-called BMS symmetries, which were known for a long time. And if you write down a vacuum that is also invariant under all the symmetries allowed, then you would never encounter such infrared divergences. There's a nice review by Andy Strominger in 2017 where you can read everything about this also in electrodynamics. So, so much for the flat space case where there are no black holes. Are there any questions here? Let me pause for a few seconds to see if everybody's on board.
Yeah, actually, I don't understand where exactly you could be normal formation. What's the condition that's telling you?
The condition that tells me that I'm forbidding it is that there is no transfer momentum transfer, and that the impact parameter is very large.
But what exactly? So where is the The large impact parameter.
The large impact parameter is not visible in the amplitude because we approximated already. I don't have an analytic expression for the amplitude in terms of the impact parameter, which you
Okay,
can
okay.
then take it to be large and then see that this emerges. You only know the asymptotic value when the impact parameter is large. So given if somebody were to magically produce an analytic expression in terms of impact parameter, if you start reducing it, you should find an amplitude that corresponds to black hole collapse. And if you start increasing it to infinity, then it should reduce to this. But the analytic expression in B or in the impact parameter is not known.
So my other question is, what happens when you go like that? What happens to the amplitude? So that amplitude is divergent.
Yeah. So I don't know. So far, to my knowledge, nobody has analyzed the iconal summation for the amplitudes in the correct vacuum. There's a recent paper last year by Strominger and Arkani Hamad where they mentioned some things, but I don't know if the exact resummation is known. What the problem is, conceptually, the problem is that the correct basis of states to be working in is not momentum basis, but it's boost eigenstates at infinity. The correct vacuum, the correct basis to be working in is boost eigenstates. And now the question turns out to be how do you represent appropriate Feynman diagrams here as correlation functions or amplitudes in the boost eigenbasis. And this particular resummation of Feynman diagrams is not explicitly known to my knowledge. There's another question. Okay. Any other questions? Okay. So where are the black holes? As I just said, if you start reducing the impact parameter by including effects that come from smaller impact parameters, it turns out that these amplitudes that we just computed, the corrections to them start to diverge. And the expectation from Veneziano and a lot of others who try to understand this problem is that they say that the fact that these amplitudes seem to diverge is a statement that we're working in a theory that is non-perturbatively far away from where black holes form. So we're looking at perturbative corrections from flat space and including perturbatively many corrections, infinitely many. But formation of black holes is a non-perturbative process. So that's not captured by these amplitudes in any direct way. And they say that, so the fact that these amplitudes begin to diverge when you start doing this is a statement that if you were to do this with smaller impact parameters, that an intermediate state would form, something that would be long-lived, like a black hole, which you would then have to treat as a new background around which you can study perturbation theory again. And as I said again, gravity is special. So there are emergent scales when you try to reduce impact parameters, like the Schwarzschild radius. So the question now becomes, how do you reduce impact parameters? And this is a complicated problem that hasn't been studied at a quantum mechanical level. People have made many attempts. One of the things that they actually tried to incorporate was they realized that classical black hole formation is very complicated. So what happens if I have some ultraviolet scale? You can think of that as a string length, or if you don't believe in string theory, then you can say some new physics appears at some ultraviolet scale, Planck scale, or something before that. What happens? You have three length scales in the problem now. So there's the Schwarzschild radius, which is governed by the energy of your collision. There's the impact parameter, which is the length scale, which tells you how far apart your infalling matter is. And then there's some ultraviolet length scale. So using these three parameters, the regime that we just computed the Feynman diagrams in the flat space iconal, is basically when B is much larger than Rs, which is also much larger than whatever ultraviolet scale. And you can start computing perturbative corrections. I could tell you a lot more about it, but I'll skip that. But just briefly, one set of classical corrections would be Rs over B. See, B is very large compared to the Schwarzschild radius. So the Schwarzschild radius over the impact parameter is small. So you can start looking at perturbation theory. That would give you corrections to the Feynman diagrams that I showed you before, which include graviton self-interaction. And including corrections which are square root of the ultraviolet scale over the impact parameter would give you vertex corrections, which are like quantum corrections. So this perturbation series has been studied to some extent, where people found these divergences. So now, to quantify large and small impact parameters, the large impact parameter regime that we've been looking at so far is that one. And the smaller impact parameter is where I want to say, where you have the Schwarzschild radius that's associated to the scattering that we perform. It corresponds, or is of the same order of the impact parameter. So you have particles. So you have particles that have a certain energy E, and we take g Newton times this energy that produces a length scale that defines for you a new length scale in the problem. And we say the impact parameter is at least of this order or smaller, but not much larger. And that's the regime that I want to study today. Any questions with the separation of scales? Okay, so how do we do this? How do we study this smaller impact parameter regime? The way I'm going to do it at a technical level in the rest of the talk is to just consider an already existing black hole and throw particles into it. And we consider scattering of these particles near the horizon. And the reason why this captures small impact parameter scattering is because the particles are interacting near the horizon. So the transverse distance between them is just the transverse distance on the sphere. So if you confine it to be near the horizon, then the impact parameter is of the order of the Schwarzschild radius, of the order of the sphere at which you're looking at. This is not a collapsing problem because I don't have a classical solution analytically to play with. That's already a bad enough problem. What I will actually need later is a propagator on the spacetime. So that turns out to be very complicated to do analytically. So that's why, as a simplified toy model, what I'm going to do is consider an existing black hole and look at scattering of particles on top of it instead of modeling a collapse. Sort of following along what Hawking did. Useful to point out. So the regime in which scattering was the iconal regime that I discussed earlier, the regime in which the ladder diagrams were dominant, was where the energies were very large, so much larger than Planck mass, for instance. Now, when you have a black hole in the game, it turns out that this condition is dramatically relaxed because you have this emergent scale of the black hole. You have a black hole mass that's already there as an infrared scale. So you can now consider energies which are much smaller than you would otherwise look at in flat space, because as long as the black hole mass is large enough, then it's difficult to violate this condition. You have to take extremely small energies to violate that condition. So the regime of validity of what I'm going to do turns out to be very large because I got lucky, meaning that there's a black hole which has an infrared scale. Another way to think of why this is a heuristic way of arguing why this may model some aspects of collapse is the following. So think of some infalling light-like matter that has some width that's going to fall in to form a black hole. An apparent horizon would already form before all the matter has collapsed. So towards the final stages of the collapse, once the black hole is almost settled, the final pieces of matter that's falling in appears to fall into what looks like an already existing horizon, because the apparent horizon starts to agree with the event horizon rather quickly towards the end. And for most of the lifetime of the black hole, because the black hole lives for extremely long time compared to the time it takes for it to form, for most of the lifetime of the black hole, any ingoing matter appears to just be falling into an already existing horizon. So the problem that I'm going to be studying is basically the red particles falling into a Schwarzschild black hole, so with some event horizon. But what I want to argue is that if you were to think of this red particle as just moving it a little further back, it would still be a good enough representation, the calculation that we're going to do, towards the final stages of collapse. Of course, if you move further back, then the horizon is just a bad approximation to the apparent horizon, to the dynamical picture of collapse. So this story is violated if you go too far back in the past, but for most of the lifetime of the black hole, this is good enough.
Is anything done in backgrounds in which there really is a collapse?
Actually, in any curved space so far, I haven't seen any calculation, which surprises me actually, because every calculation that I'm doing in the rest of the talk could have been done essentially in the 70s or 80s. There's no new technology that needed to be developed later on that I'm going to be using. So it's sort of, one of the complications is that people just didn't believe that you could invert the quadratic operator for the action to find the propagator, even in some limit in the Schwarzschild background. It turns out that if you're careful enough, you can invert and find the propagator close to the horizon. It looks like a horrible mess when you start out, but then if you observe that the horizon itself is conformally flat, has some conformal prefactor and it's flat on the sphere, then you start seeing why there could possibly be a propagator that you could work out. But once you start working it out, it seemed like we could do it. But yeah, so to my knowledge, the reason why it hasn't been attempted is just because it looks deceptively complicated. So I've set up enough to explain what I mean by black hole scattering, where, as I just said, we're going to look at the background field method again, but instead of perturbing around flat space, we're going to do this around the Schwarzschild metric. And now your gravitons are now fluctuations of the background, which is the Schwarzschild metric, and not flat space. Interactions will again be generated by a cubic vertex where the graviton talks to the stress tensor. Now, I forgot to mention in the flat space case, but every time you compute any physical observable, you have to gauge fix in a gauge theory. The graviton has too many degrees of freedom. So the standard thing to do is to fix the covariant gauge or the Dedombra gauge when in flat space. The difficult problem here that we're faced with is that if you employ the Dedombra gauge, the quadratic operator is not invertible analytically. The only symmetry that we're left with is a spherical symmetry of the solution. So you'd like to exploit it, but the Dedombra gauge couples all the different partial waves. So one has to come up with a different gauge. And Reggie and Wheeler had a really beautiful paper in 1957 where they employed a new gauge called the Reggie-Wheeler gauge now, where the graviton is split as follows. This looks like a very bad thing to do because you lose a lot of covariance. But what I'm going to do is to integrate the sphere out. So we'll be interested in essentially the light cone or the longitudinal part of the metric with LM indices for every field in the theory. It's like expanding the scalar field in partial waves. But because this is a tensor, spin-2 particle, you have to be careful with how you split it. In particular, the angular dependence is not only in the cycle harmonics, but in the tensor itself, you have some angular dependence that shows up to represent that this is a spin-2 field. But it can be done. Reggie and Wheeler did this. And this gauge essentially has, so we have 10 degrees of freedom in the graviton, and 4 of them have to be gauge fixed. So in this gauge, you see that HAB is a 2x2 symmetric matrix, so it has 3 degrees of freedom. K is a transverse scalar, so that's 4. And this is called an even mode, and the other one is odd. So this is block diagonal, the other one is off diagonal, and X carries 2 degrees of freedom. So that makes up your 6 physical off-shell degrees of freedom that will contribute to Feynman diagrams. So once you write your theory in this gauge, it turns out that the quadratic action decouples all these different harmonics. So you can integrate the sphere out and study essentially an effectively 2-dimensional theory for each partial wave. A technical observation is that as long as you have low transverse momenta, so if you're looking at the physics in the longitudinal directions, just like before, the odd parity graviton does not contribute. So I'll just be focusing on the even parity mode for the rest of this talk. So we put this graviton in this strange gauge, and the price you pay is that all the different fields H and K coupled to each other already at quadratic order. So you don't have these are not the diagonal degrees of freedom, so to say. So you have a propagator, you have a quadratic operator that just couples H's, but there's also the other one, H talks to K and K talks to H and so on. So your propagators are defined by this complicated matrix equation, and you have to find all the propagators for all the tensorial modes. In general, I haven't done anything so far. I've just written the entire theory in a weird gauge. So the problem is no more solvable now than before. The magic now comes into going near the horizon next. We will be able to solve for these propagators in the near horizon limit. So in the near horizon region, if you look at this metric, I'm going to say R is roughly constant, the Schwarzschild radius. So this becomes a product space. And therefore, you can approximate, and you already see that the longitudinal metric is now conformally flat. So it's flat with some conformity factor. And in the near horizon limit, this factor A also simplifies for the Schwarzschild metric. And here are the Feynman rules that you can derive. This is a long calculation that we've detailed out in our paper. So I'll spare you the details, but here are the Feynman rules. I've written only one of the propagators, the tensorial one. There are 2 others, which actually have more physical degrees of freedom, but this is the one that will be important for now. So notice that the propagator has this complicated looking form, but also not really. There's because the spacetime is conformally flat, you see something that looks like a flat space propagator. There's some momentum dependence in the next term there. And now if you set your momentum to 0, you don't have a pole in this theory. This thing is infrared safe because there's a prefactor which has a Schwarzschild radius sitting in there. So the emergent scale appears in the propagator, already in the infrared limit when you send k to 0. There are UV divergences that you expect from non-renormalizability in the theory by just summing over all the partial waves that you have. So we haven't solved any problems with quantum gravity in the ultraviolet, but in the infrared, you have a well-behaved theory. But as I said, the graviton behaves like it has an effective two-dimensional mass. The 4D graviton is still massless. You haven't changed any of the physical properties of the theory. It's just because of the curvature artifact that you end up having something that looks like a massive graviton in 2 dimensions. The scalar particles also were massless in 4D, but because of the curvature, they end up having a tiny mass, which is proportional to the partial wave in question. So I just split out a spherical, an S wave for the scalar field, and I represent that with a dotted line, such that at every vertex, in principle, you would have all the angular moment, all the partial waves that mix through Klebsch-Gordon coefficients. But in principle, that can be put in here, and you can work out everything that I'm going to say later. But just so the formulas look simpler, I'm just going to assume that at every vertex, I have one scalar particle that has a fixed angular momentum. So for simplicity, I just put it in the X way, such that the L's just carry on to only one of the legs. So it's an unnecessary technical simplification. But the important point is that the vertex is now governed by an emergent coupling constant, which is no longer just G Newton, but it is m Planck over m black hole. So this theory is valid, this effective theory is valid as long as this coupling constant is small, so that you can work out perturbation theory in this non-perturbative saddle. And this is true whenever the black hole is large compared to Planck science.
So, sorry,
Yes.
so you can also, there's an effective mass that's scaled by 1 over the structure. So you can only trust the description around the structure around the black hole.
Correct.
Then you're right.
Correct. Yeah, I'm agnostic of whatever happens inside the black hole, because I'm just looking at the scattering problem is something that you set up at infinity or far away. So you send something in, there's some potential, it interacts in a complicated way, and you get something out. So I'm interested in what happens to the asymptotic observer, the observer that's far away. And I'm saying that you can treat this to leading order, you can treat these particles to be asymptotically free, except when they reach the horizon. In the near horizon region, there's this effective coupling, there's some interactions, and the scattering matrix is governed by the effective theory near the horizon.
Now, how are you going to match incoming states since you want to be information?
Yeah, so that's a problem we haven't solved. The asymptotic states that I'm looking at here are asymptotic states in the near horizon region. So you want to, it's also interesting because think of a constant, an observer at a constant distance from the horizon. Right? If you trace this observer all the way back near the horizon, it looks like the asymptote towards the horizon, but also infinity, and the same in the future in the conformal diagram. So that's roughly the observer that I'm thinking of. So there is a notion of infinity for the near horizon observer, and how you map these states to those states outside that are defined in your Fock space at infinity, that's a problem we haven't solved yet. So an important subtlety here is that there are some gauge redundancies in this theory that we haven't quite fixed. So for example, look at the L equals 0 mode. This sign flips for the S wave. For L equals 1, there's a pole in there. And this is not a physical pole in momentum space. It's a pole because of the angular momentum. That's just a sign that there's some gauge subtleties in the theory that there's additional redundant gauge symmetry that you have to fix for these two. And there's some group in Stanford that has pointed this out. And we've also worked this out in one of our papers. And we're going to write down all the propagators in an upcoming paper, taking into account all the gauge subtleties, but they're not important for what I'm going to say. No, doesn't have to be the last.
It's not going to be one.
Great.
So we know very well how to solve this problem in the regular value. So why can't we do that here?
I'm not sure.
Solve the problem in the first place.
Presumably one can, but maybe this is a good point to discuss a few slides down when you see some of the expressions that I'm going to write down. So just to understand conceptually what's going on, we now have 3 scales in the problem. Now I'm just writing down everything in terms of mass scale. So the Planck mass, the black hole mass, and the energy of the collision that we're interested in. And as I said, we're going to look at perturbed regime where the energy times the black hole mass is much bigger than Planck mass squared. The consequence of this will be that in the 2-to-2 diagrams that we're computing, the dominant diagrams turn out to be the ones where the graviton that's exchanged is soft. But we're going to sum over infinitely many Feynman diagrams in the ladder in a ladder sense. And so that means that we're going to have a non-perturbative result in this coupling constant gamma, or perturbatively exact result in gamma. To summarize the regime of phase space, I'm just repeating myself so that it's hopefully clearer and clearer. So we said that if transverse momenta are low, then the different partial waves do not mix to leading order. So there's a separation of longitudinal and transverse effects. And we wanted to capture effects associated to small impact parameter. So that means that we're looking at scattering near the horizon. And because there's an emergent scale, the energies, the regime and phase space that the calculations are going to be valid is much wider than you would have expected from your flat space intuition. And using this, I'm going to show how to compute some of these scattering amplitudes in the next section. Any questions so far? Okay, so just like before, I'm just going to compute some of these diagrams, and these turn out to be relatively simple or analogous to the flat space case because the metric was conformally flat, as I said, in 2D, in the effective two-dimensional theory. And you end up with expressions which look like this. So the n-1 loop amplitude, where n gravitons are exchanged, can be written in terms of one function chi. And now notice that everything is in 2 dimensions because I've already integrated out the sphere, and everything here should in principle carry an LM index to represent the partial wave in question. And this chi is called the iconal function. It has this form where this is dominant, or this amplitude is dominant for the low L modes, where L is very small. So just like in the flat space case, you could compute this amplitude for an arbitrary loop diagram. And if I'm going to compare this iconal function in flat space to the one that you have for the black hole, in flat space, the highly spinning modes are the dominant ones. So the physically new effect that you find in this case is that the low L modes are dominant. This is a statement that the perturbations of the metric that govern these scattering amplitudes are spherically symmetric to leading order because the solution itself is spherically symmetric. And these amplitudes can be resummed. So I just sum over all loop exchanges, and this neatly exponentiates, and you get a pure phase for the scattering amplitude, which is a 2x2 amplitude. So perhaps you can already notice this from here. Chi has no k dependence, momentum dependence. So this integral is going to project us into the soft sector where k is projected into 0. You get a delta function from this integral. So in the end, that means that the n loop amplitude is dominated by the soft sector of the speed of the propagator, the k equals 0 sector. So one of the things you could say is, if I were to do a better computation, numerical or otherwise, somebody more powerful just gave me a better expression for the propagator globally and not just in the near horizon region. In the end, that would just change the zero momentum factor, which turns out to be a constant in this case. So you would change what that constant is, but the exponentiation and the results would sort of remain. So the physics is captured already to leading order before one performs an exact calculation of the propagator. Presumably one can extract more physics if one does a better calculation. So this is sort of the first back of the envelope, not really, but the first order calculation that you would do. There's no reason why, if you throw 2 particles into a black hole, that only 2 should emerge. In fact, Hawking told us that you'd get a large number of particles with the thermal spectrum, right? So the amplitude that you actually want to be considering is not just a 2 to 2 amplitude, which is actually heavily suppressed, but actually a 2 to n amplitude for some arbitrary n. And with the Feynman rules that we have, one could compute these, and we've done that. So at tree level, you find this amplitude, which has a nice form, and it's actually very interesting because this amplitude is sharply peaked around some maximum value of n. So it tells you that the dominant value of n is determined by the dynamics, and that's given to be g times e squared. And if you consider the energy of the scattering to correspond to the Schwarzschild radius of the solution, that turns out that this n max corresponds to the number of operators that gives you the entropy of the solution. So it tells you which n dominates. And the other way to think about it is that if you have a black hole that's decaying, the number of microstates into which it will decay is given by this multiplicity, which corresponds to a definite value of n. This is just from the tree-level diagrams. One could actually include additional ladder corrections here. That gets a little more complicated because you have, in general, arbitrary exchanges in this theory, which are very difficult to compute. But we were able to compute a class of infinitely many loop corrections to this, which give you oscillations, like pure phase oscillations that we saw in the 2-to-2 example, on top of this real factor. So you have a dominant real factor, on top of which you have oscillations that correspond to all the loop corrections. So the statement is that in the 2-to-2 example, we just saw pure phase oscillations of this amplitude. But as the dominant contribution to the scattering process comes from a large number of n, which gives you a real factor to the amplitude and then some imaginary pure phase oscillation. From these oscillations, you can ask what the time delay is. What this means is, take any scattering problem in quantum mechanics, for example. You send a wave to scatter against some potential. Depending on how complicated the potential is, the particle is going to spend a certain amount of time, and then before it returns to you at infinity. There's a way to characterize, given the scattering matrix, what that time delay is. And this depends on how complicated the potential is. So it sort of characterizes for you the interacting potential. And this was a concept introduced by Wigner in the 30s. And there's a beautiful PhD thesis of Heisenberg also in the 30s, I believe, where they discuss this. And it can be understood in a very simple way. So let's consider the scattering matrix near some resonance E0 with some positive width E. By definition, the fact that this is a resonance means that the S matrix has to have a pole. So if you put E equals E0 in the real space, there's a pole. And the fact that this is a pole means that alpha cannot compete with this pole. So this is some slowly varying function of E in general. And the time delay is defined to be the imaginary part of the energy derivative of the log. Yes, thanks. Great. So the energy derivative, the logarithm you can think of as taking, imagine you have an amplitude that's a pure phase. This logarithm essentially pulls down the thing in the exponent. The imaginary part kills the I, and you end up taking the derivative of the factor that captures the dynamics. And now if you take this thing for the scattering matrix and you go near the resonance, you see that the time delay is given by 1 over E, which gives the lifetime of the resonance. So it tells you that if you have some scattering problem, this time delay is going to capture how the lifetime of the intermediate state. Right, so now you can apply this formula to the amplitudes that we computed. In the elastic scattering, where you have 2-to-2, you compute this and make sure that you're working in the right coordinates and so on. You find that the time delay is given by m log m. I'm a little sloppy with dimension, but this is a universal factor, and the universality associated with this time delay was attributed to theoretic macroscopic properties of the horizon. But the argument was given in these papers by Stanford and CENTRA and then Maldacena with the same author, where they argued that the black hole, if you throw whatever two particles into this black hole, as long as you're considering elastic dynamics, that the black hole is going to behave in a universal way no matter what you throw into it, and it's going to scramble this information of the two particles that you sent in some universal way that captures for you, that is captured by the scale of the problem, which is the black hole mass. If you compute the time delay when you have n number of particles, it turns out that this is a much longer time scale, and this is because the tree-level amplitudes for large n also grow exponentially. So you beat the log, and you end up with a polynomial behavior. And this is called the page time. So this is called the scrambling time. This is called the page time, or the half-lifetime of the black hole. This is a relatively small amount of time, but this is huge for a given mass, that it scales polynomially. So the statement now is that if you were to throw two particles in and you ask how long do I have to wait before information returns, that time turns out to be page time or half lifetime of the black hole. And that also means that after the black hole has evaporated half of its mass, or if you wait for half lifetime of the black hole, free field theory is no longer valid because you have a lot of information that's coming out from the dynamics that you're ignoring. So Hawking's free field theory breaks down after page time. I'm towards the end of my talk. Are there any questions? Yes.
So when you mentioned the two-way sampling process, you said that the sharp. Can you go back to that slide?
Yes.
This is really useful question. And so, is there something missing? There's units on the right hand side. So this is the number of, if I understand, the number of particles that do this process where it's split.
Yeah, exactly.
So there's units on the.
This goes as length squared, and this is energy squared.
Yeah.
So this is dimensionless. This is also dimensionless. Right?
Oh, then we're-
I mean 4 dimensions. So G is Planck length squared. So this has.
Oh, you're setting H one.
Yeah.
Oh,
Sorry.
okay, sorry.
Yes. H is always 1.
No, it's not.
Right. So in the last few minutes, let me quickly run through a couple of applications. So the first one is what I mentioned all the way at the start, which is of gravitational echoes. So classically, if you throw some wave or some perturbation past the light ring or the potential barrier, a part of it would go in, a part of it would get reflected, and there is nothing coming out. So you just have infalling boundary conditions. Now, Hawking said that in the free field theory already, you would have some completely uncorrelated mess that comes out. Now, what we find is that actually there's some correlation between what comes out and what goes in, and that correlation is governed by the graviton exchanges. And you see the 2-to-2 Feynman diagram already here. So essentially, one way to now think about it is that the ingoing wave, as it falls in, produces a graviton. That graviton produces something that's coming out again, right? And now you have an echo that shows up from the other side of the barrier a little later. And this keeps happening because of the backscattering that will keep happening. This is very similar to what would happen if you had a horizonless compact object here, which has some cutoff. But the interesting thing is that these echoes are produced in this theory where I've introduced no new free parameters. Everything is governed by just h bar, Planck mass, and the black hole mass. So there's no free parameter that allows me to tweak how these echoes leak out. So if there's some measurement that can measure these echoes, then this theory is falsifiable.
So we can calculate that.
Yes, you can calculate these echoes, and there's a paper that where we wrote down these echoes just like you would for the compact objects, and the formulas are analogous. I don't remember the details off the top of my head, but we've written a paper in 2012 with Panos Betsios and Papadulaki, where we worked out the spectrum of these echoes and the relative amplitudes for succeeding echoes. As a last application, let me say something about Weinberg's soft theorem. So the soft theorems are the following statement. Consider some arbitrarily many or n to m scattering problem. And now let's, whatever the amplitude is, let's not calculate that, but let's just consider this process. Add to it an extra graviton that's coming up. Weinberg showed, and it's in his book, chapter 13, that the dominant contribution to this comes from two diagrams. One is when one of the outgoing legs spits out as graviton, and the other is when one of the ingoing legs spits out as graviton. This is when the graviton momentum is small, so soft. So in this near soft limit, you see that the extra contribution to the original amplitude comes from basically this vertex and the virtual propagator. Now, if you take this q to be very small, that means that p prime k is anyway on shell because it's an external leg. But if you take q to be small, then the internal propagator also goes on shell. So you end up with a pole. And what Weinberg showed is that this amplitude with this extra soft graviton has this nice factorized property that it's given by the old amplitude, whatever that is, multiplied by some soft prefactor. And this is Weinberg's soft theorem. And this is to leading order in small q. And there are infinitely many such soft theorems as you go to subleading order and so on. And each of these soft theorems has actually been shown to correspond to ward identities associated with the symmetries at null infinity. This was the breakthrough results of Strominger and collaborators in the last decade. And as I said, this arises from the soft limit where you send Q to 0. But we haven't set Q to 0, we're expanding near 0. And now Q is a dimension full quantity, so you should be worried. What does actually Q to 0 mean? And it's actually simple. There's only one infrared scale, or sorry, ultraviolet scale that's available. So what we mean by Q to 0 is basically sending implying to infinity. That's also the theory, that's also the limit in which the perturbation theory is valid. Now, if you go to the black hole case, you cannot naively take this soft limit, because if you send implying to infinity, you have to specify what happens to the black hole mass, which has to be bigger. It turns out that you can define a new emergent soft limit for black hole, where you say that you can send implying to infinity, provided that this goes to 0 faster. So this is an additional constraint. So this is sort of an emergent soft limit that appears when you have a large black hole in the game. And in this limit, you can produce, one can write down soft theorems that emerge near the black hole that are governed by the Feynman rules that I wrote down earlier. And these are emergent soft theorems that are valid as long as the black hole is very large. And they may have something to do with near horizon symmetries analogous to symmetries at null infinity. And this is something that I'm working out now with Ankit, who's a student in Brussels. View of time, let me skip the last slide and let me conclude here. So what should you take away from this talk? Hopefully a few things. One is that there seems to be a remarkable new phase in quantum gravity, which captures black hole evolution with dynamics of the horizon incorporated. The information paradox seems to be addressed, where I have made no assumptions of what the ultraviolet behavior of the theory is. There are emergent soft theorems near the black hole horizon, which are analogous to but different from Weinberg's soft theorems in flat space. There are gravitational echoes that arise because of the dynamics of the horizon, which is a parameter-free, which has no new parameters in the game. So it seems to be predicted by a minimally coupled scalar to the Einstein-Hilbert action. And the last thing is something that I didn't mention. And here's something that one can push this program further with several ideas that include, for example, you can compute subleading corrections to all the amplitudes that I've looked at and look for whether this gives you a hint of what ultraviolet physics one should be looking for. You can include additional fields. I just looked at scalar fields, higher order corrections. Nobody tells me that I should stop at the cubic vertex. I could go all the way up, and there are infinitely many such. I showed you a picture of what the echoes look like in the elastic scattering picture, which has some universal timescale associated with the echo spacing. But there's particle production, which is actually the dominant picture in this regime. And one can ask what the echoes look like for when there's particle production in the game. There are subleading soft theorems that can be worked out as corrections to the leading soft theorems that I wrote down. There's another very interesting case where there's an emergent scale in the infrared, which is the cosmological horizon. So this seems to suggest the dynamics of the cosmological horizon probably also reflect some sort of observable that can be computed in the effective theory. With that, let me stop and thank you and take some questions.
Thank you. Thank you for your very nice talk.
Thank you.
Do you possibly believe the possible, let's say, oscillational constant you can work from the field and get like probably a bit about it eventually? Have you maybe believe if you put some constraints to this kind of problem? Am I right or they are far away from
I actually don't know. A lot of the things that I haven't looked at any observational consequences in any detail, to be honest.
But do you expect that to be very small?
I would expect them to be very small. However, there's something, now that you mention it, there's something that may be strong enough. Before merger, in compact merge, in binary mergers, the dominant amplitudes that are computed here are the ones which are heavily spinning. And what I'm told from some talks I've heard from Thibaut Damour is that the scattering amplitudes seem to capture the pre-merger phase of this amplitude. These amplitudes seem to capture the pre-merger effects. Once the merger happens, the process is violent and the perturbative theory around flat space is no longer valid. But now that physics was dominated by the large angular momentum mode. But post-merger, once the thing is settled down, it seems that you can replace all your scattering amplitudes with the graviton propagator on the black hole background, where you're now the physics is dominated by the low angular momentum mode. So there's a natural post-black hole approximation like the post-Minkowskian, which may show up. I don't know how strong these signals are, and I have no intuition for how to compare them against what is observed. But this is the first place I would look.
Any more?
So these are new software theorems that you get. You have them because you are asymptotic flat space, or if you don't have this regime asymptotic regime, you also expect.
I actually think that the theorems are agnostic to the asymptotics because I'm focusing on the dynamics of the physics near the horizon. So as long as you are in a Schwarzschild background or something that's not supersymmetric or extremal, as long as you have a physical black hole, I expect that these emergent soft theorems would arise also in ADS or in non-asymptotically flat spaces, because the asymptotics have been decoupled in the near horizon limit where I'm computing these Feynman diagrams. Yeah, I think the physics of it is governed by this soft limit here. This probably gets modified slightly with the parameters that are new parameters in the curve black hole. But I imagine that something like this should be valid, because this is sort of very universal, the way you can write down an emergent soft limit.
Really be very different.
That you see, I mean, all the amplitudes are gauge invariant. I just used the Regulator gauge for the black hole, or for the Schwarzschild black hole, because it's the only one where I could compute. But in the end, the physics has to be gauge invariant.
There's a single calculation also in the extreme. No, but at least no, it was the first. Thank you.
Thank you.
Okay, does anybody else have a question?
I'm still on this also not on the part. Even in a long shot, if you have this kind of, you mentioned that eventually in some particular case you get some kind of signature on our that could be macroscopic, although we don't know the content. The other question that was going to imagine some kind of electromagnetic photograph all of these processes. Well, basically, that is what the evidence of
Yeah, I don't know.
Well, with that, let's thank Nava.
If you enjoyed the video, like and subscribe.